Hello and welcome. Today we'll be taking a deep dive into a perspective piece by Rigoberto Advincula and Jihua Chen titled Towards AI/ML-Driven Optimization of Dendrimer Design, Synthesis, and Applications. This work explores the exciting and challenging intersection of polymer chemistry, specifically the world of dendrimers, and the rapidly advancing fields of artificial intelligence and machine learning. The central premise is that AI and machine learning, or AI/ML, hold immense potential for revolutionizing how we work with complex materials like polymers. The properties of these materials, from their chemical composition to their molecular and macromolecular structure, ultimately determine their real-world function. The challenge has always been to predict and control these properties. Traditionally, this has relied on extensive experimentation and deep domain expertise. However, we are now entering an era where we can augment our data sources, like scientific literature, with powerful tools like large language models, or LLMs, using techniques such as retrieval-augmented generation, RAG. These augmented datasets can then be used to create machine-readable descriptors that inform new molecular designs and even predict optimal synthesis routes. This paper specifically highlights the advances in dendrimer materials. These are a unique class of polymers with applications in nanomaterials, energy, drug delivery, and sensors. The authors aim to lay out a path for enhancing our ability to predict their properties and ultimately to automate their synthesis in what are known as autonomous self-driving laboratories. So to begin, let's establish a clear understanding of what dendrimers are. They belong to a broader class of hyperbranched macromolecules. The name itself comes from the Greek words dendron, meaning tree, and meros, meaning part. And this tree-like structure is key.
Unlike simple branched polymers, which can be random, dendrimers are composed of monomers that grow in a mathematically precise exponential way. You can visualize this in two primary ways. In a divergent approach, the structure grows radially outwards from a central core. In a convergent approach, the branches, or dendrons, are synthesized first and then attached to a central core.
This precise generational growth gives them a globular, nanometer-sized structure. They are often classified by their generation number, G1, G2, G3, and so on, which indicates how many layers of branching units radiate from the core. As the generation number increases, the dendrimer grows, but steric hindrance, or crowding of the branches, eventually limits its size. Because of their well-defined structure, high surface area, and the ability to pack in a large number of functional groups on their surface, they behave more like nanoparticles than traditional entangled linear polymers. Their interior can be designed to be hollow or cavernous, creating what's known as a dendrobox that can encapsulate other molecules, like drugs. The surface itself can be highly reactive and tailored for specific functions. This versatility makes them incredibly powerful. The synthesis of these perfect or near-perfect dendrimers is not trivial. It requires precise control over the chemistry, often involving iterative steps of protection and deprotection of reactive groups. Monomer design is crucial, using building blocks with specific functionalities like AB2 or A2B, where A and B represent different reactive groups. The choice of monomer, branching architecture, and even the type of bonds used, covalent or non-covalent, all contribute to the final multifunctionality of the dendrimer. A classic and commercially available example is the polyamidoamine dendrimer, or PAMAM. Its structure, bearing a triethanolamine core, showcases the repeating amide linkages and the dense packing of terminal amine groups on its surface. These terminal groups are highly reactive and are key to applications like bioconjugation for drug delivery and medical imaging. The unique structure of dendrimers leads to a unique set of properties. They typically have low viscosity and high solubility compared to linear polymers of similar molecular weight. They can act as amphiphiles, ligands for catalysts, or even mimic the function of viruses and enzymes. The authors have extensive experience in this area, and they share several examples from their own work to illustrate the sheer versatility of these molecules. First, they discuss polythiophene dendrimers. Thiophenes are building blocks for conjugated polymers, which are materials that can conduct electricity. The researchers synthesized the first all-thiophene dendrimer using a convergent approach with an AB2-type thiophene monomer. Using techniques like AFM, or atomic force microscopy, they were able to directly observe the individual dendrimer nanoparticles. They further functionalized these structures, for example, by placing a ruthenium-2 complex at the core, which created a dendrimer that could fluoresce in the near-infrared region. Another variation involved a porphyrin core, which led to interesting aggregation behaviors that were dependent on the dendrimer's size and concentration. Building on this, the authors explored the creation of hybrid nanomaterials. They used polythiopene dendrins as capping agents to synthesize and stabilize nanoparticles, such as cadmium selenide quantum dots. In these hybrid systems, the organic dendrin shell can interact with the inorganic nanoparticle core, leading to useful properties like energy transfer. They also demonstrated how a PAMM dendrimer could act as a dendrimer box or a nanoreactor. By functionalizing the surface of a PAMM dendrimer with thiopene groups, they were able to encapsulate and form metal nanoparticles directly within the dendrimer structure. Another important functional group they worked with is carbazole. Carbazoles are known for their hole transport properties, making them valuable for electronic devices like organic light-emitting diodes, or OLEDs. The authors developed a high-yield convergent synthesis for dendrons with carbazole groups on their periphery. These dendrimeric precursors could then be cross-linked, essentially locking them into a rigid nanoparticle structure. They even created double-layered dendrimers with a symmetric core and different functional dendrons, designing materials that could be patterned using light or electricity. This work extended to star-like copolymers, where a dendrimer core initiates the growth of polymer arms, which can then be used for applications like the controlled release of dyes or model drugs from nanosheet films. The final example highlights a class of all-azobenzene dendrimers. Azobenzene is a molecule that can switch its shape from a trans to a cis form when exposed to light. By incorporating up to 29 of these units into a dendrimer structure across 4 generations, the authors created a highly photoresponsive macromolecule. This was achieved using a convergent method involving the condensation of protected nitrosyl compounds with 5 amino isopolic acids. These materials could then be studied as thin films, whose dielectric properties could be precisely controlled with light. These examples collectively demonstrate the incredible design space and functional versatility of dendrimers. However, the authors emphasized that achieving these results required careful planning, long experimentation, and trial-and-error optimization based on deep researcher experience. This is precisely where the field needs to evolve. The immense body of existing work must be brought into the modern AI/ML paradigm to accelerate discovery and unlock commercial potential. This brings us to the core of the paper's perspective, the integration of machine learning and polymer data analytics. The traditional trial-and-error approach generates a lot of data, but it's often in varied formats and relies heavily on human input. The goal is to move towards dendrimer informatics, where ML-driven models can analyze existing data to guide future experiments. To understand how this works, it's helpful to compare the different AI paradigms as they apply to material science. First, there is traditional machine learning, or ML. This typically involves using descriptive or predictive models on structured, tabular data. For example, you could train a model to predict a material's performance based on a set of known chemical features. These models are great for tasks like hyperparameter optimization for experiments or feature selection in chemical compositions. They are relatively fast and can democratize analysis for non-coders. Next is deep learning, or DL. This uses hierarchical neural networks for more complex, high-dimensional data, like images or spectra. In material science, DL is used for tasks like predicting crystal structures, reconstructing atomic contact maps from simulations, or processing microstructural images. DL models can capture complex, nonlinear relationships that traditional physics models might miss. However, they require large-scale, high-quality datasets. Finally, we have generative AI, or GenAI. This involves probabilistic modeling to create entirely new material configurations that don't exist in the training data. This is incredibly powerful for inverse design, where you start with a desired property and ask the model to generate a molecular structure that exhibits it. Generative models can exploit the infinite chemical space beyond known databases, but they require high-quality training distributions to ensure the generated structures are physically valid. To apply any of these models, we first need to solve a fundamental problem: translating chemical structures into a language that machines can understand. This is where chemical descriptors come in. A common representation is SMILES, which encodes a 2D chemical structure as a simple line of text. This text string can then be converted into a numerical vector that a machine learning model can process. For complex macromolecules like polymers, we need more sophisticated descriptors that can capture not just the repeating unit, but also the hierarchical and topological features, things that are especially important for branched dendrimers.
Advanced platforms and fingerprinting methods are being developed for this, including polymer-specific natural language processing models, like Polybird, which is a deep learning model trained on polymer smile strings. With these tools, we can begin to build models that predict the complex structure, composition, processing property relationships of dendrimers. However, the quality of these models depends entirely on the quality and quantity of the data used to train them. The existing literature is a vast source, but data is often inconsistent due to a lack of standardization in experimental conditions and reporting. This is where the concept of the self-driving laboratory, or SDL, becomes essential. An SDL is an automated platform that closes the loop between synthesis, characterization, and decision-making. Instead of a human scientist performing each step in series over weeks, an SDL can run experiments, analyze the results, and decide on the next experiment to run, all within hours. A typical SDL for chemical synthesis might use a continuous flow reactor, where reagents are pumped through tubes and mixed under precise control of temperature, pressure, and time. Mechatronic systems like liquid handling robots can autonomously select and mix different reagents based on an algorithm's instructions. A suite of inline analytical tools, like spectrometers for UV-Vis, infrared or Raman spectroscopy, and chromatographs, monitor the reaction in real time. The brain of the SDL is an ML workflow. Algorithms like Bayesian optimization can be used to intelligently explore the vast parameter space of a reaction. Instead of testing every possible combination of conditions, the algorithm uses the results of previous experiments to predict which new set of conditions is most likely to lead to an optimal outcome, such as higher yield or purity. This allows the SDL to efficiently find the best synthesis route with a minimal number of experiments. The authors provide a powerful illustration of this with the ADA self-driving laboratory. In one workflow, ADA's goal is to discover a thin film composition with the highest possible charge mobility. The robotic arm first mixes an ink from stock solutions of a whole transport material, a dopant, and an additive. It then spin coats this ink onto a substrate, anneals it with a heat gun, and then moves the sample through a series of characterization stations. A camera records an image, a spectrometer measures its optical properties, and a 4-point probe measures its electrical properties. This data is fed into an orchestration software, which uses a Bayesian optimization algorithm to design the next experiment, what concentration of chemicals to mix next, to continue the search for the optimal film. This entire cycle, from synthesis to analysis to decision, is automated.
This same principle can be applied to dendrimer synthesis. By implementing continuous flow chemistries for the iterative growth of dendrimers, an SDL could rapidly explore different monomers, reaction conditions, and purification steps, all while generating clean, standardized, and hallucination-free data perfect for training the next generation of AI/ML models. So how does this all come together for the future of dendrimer science? The primary goal is to codify the language of dendrimers, accelerate the science, and scale up the research and production of these powerful nano-macromolecules. This requires moving beyond the traditional literature-based approach. We can see this shift visualized in a comparison between traditional nanomedicine research, which is often fragmented, based on small sample sizes, and difficult to reproduce, and a nanoinformatics-based approach. The informatics approach relies on centralized, large-scale databases with standardized protocols, enabling predictive modeling and truly rational AI/ML-driven design. There are already promising applications of this in the biomedical field. Researchers are developing workflows to predict properties like the cytotoxicity of dendrimers. By extracting data from literature, generating 3D molecular structures, and calculating a wide range of molecular descriptors, they can train machine learning models to predict how toxic a given dendrimer will be. Advanced analysis techniques can even identify which specific features, such as charge, surface area, size, or mass distribution, are most influential in determining that toxicity. This allows for the in silico design of safer and more effective dendrimers for applications like drug delivery. To achieve this on a broader scale, the authors argue that we need to demonstrate more continuous flow chemistries for dendrimer synthesis within SDLs. The data generated from these automated platforms will be crucial for training more advanced models. In conclusion, the path forward for dendrimer science, and indeed for much of polymer and materials science, lies in the tight integration of automated experimentation and artificial intelligence. The authors envision a future where ML-driven self-driving laboratories, guided by expert scientists and an expert-in-the-loop framework, can rapidly generate and compile high-throughput data. The models used won't just be black boxes, they will be physics-informed, grounded in the first principles of macromolecular theory. These models will guide experiments, whether for optimizing known reactions or for discovering entirely new dendrimer microstructures. This will allow us to tackle the immense design space of these molecules, considering synthesis routes, composition, macro initiation, and hybrid structures, with a level of efficiency we've never seen before. The ultimate challenge, and the greatest opportunity, is to use these new tools to finally scale up the production of dendrimers and achieve the commercial viability that their remarkable properties have long promised. This work provides a compelling roadmap for how we can get there, powered by more advanced data analytics and intelligent autonomous systems. Thank you.